Okay, now that we have introduced rotation, we have two force laws. One is the one we're most familiar with, Newton's second law, written as F equals ma. Careful to recognize it's a vector, and careful to indicate it's the net forces acting on the object. It will cause it to accelerate along a line. And now we have the rotational equivalent, which is the net torques, also a vector, acting on an object with extended mass, which we represent that mass with a moment of inertia, and it will rotate, okay, with an angular acceleration alpha. Okay. Now, with these two problems, there is a huge set of problems that's called statics, meaning nothing's moving. So like if you want to analyze a bridge, well, your goal really is that the bridge doesn't move. Or a building, you don't want that building to move. And in that case, you want it to not only is the velocity or the acceleration zero, not just because it's not changing speed, it's not moving at all. And so in that case, we have conditions of static or equilibrium. And so when we consider equilibrium, those go to zero, and we can apply these two laws to a whole bunch of problems. And this together gives us a lot of power to solve these problems. Okay, so for example, if I want to look at something standing there, so like I've got a ladder leaning up against a wall, okay, and it's just sitting there. Well, I could ask all sorts of questions about, what is the force of the ladder against the wall? What's the force of the wall pulling up on the ladder? Okay, what is the force of the ground pulling in on this? Because obviously, if these are frictionless, then that ladder would slip. Okay, but because of the friction, it's able to kind of pivot itself right there. So we could ask all sorts of questions, and thing is we can apply, well, there's no net forces, which means all the horizontal forces on the wall and the floor must cancel each other out. So whatever this force is, this normal force here from the wall on the ladder, it must be equal to the frictional force here on the ladder from the floor. Okay. Likewise, here's a normal force pushing up from the floor. Okay. So we'll do normal wall and normal floor. There is a gravitational force pulling down, and there must be a force acting on this wall, most likely pulling it up a little bit. Probably not too big of a force, but it would be there. So there'd be some static frictional force pulling up on the ladder. And so this upward normal force plus this upward frictional force must equal this downward force of gravity, because the net forces must equal zero. So we can apply Newton's second law to the two dimensions here. So we basically have two equations to work with here. Now we also have this one. Now this one's a little bit more unique, or more interesting, because we have all sorts of ways that the net torque could be zero. Okay? And what's important is this is net torque about some point. Okay? So when I'm looking at this problem that's not moving, well, what's that point? Generally, when we're doing rotation, we see I have a wheel spinning. Oh, well, that makes sense that that's the point of reference, the torque about that point where it's spinning. But when it's not spinning, what do? Where's your point, your reference point? That's the beauty of this, is no matter which point you take, if it's not moving, it's not accelerating about that point. Okay? So this is true for any point. So I could pick the base of the ladder to be my point of reference. And if I do, and I consider the net torques, remembering that torque is RF sine of theta in its basic form. Okay? Well, R is the distance from the reference point to where the force is being applied. Well, if I pick this point to be my reference point, then guess what? The torques due to this frictional force and this frictional force are zero, and say that they won't factor in. So if these are some unknown forces, well, guess what? By choosing that point to be here, my reference point to be here, I don't have to worry about those. They won't be in my equation. Now, these three will, okay? Those three will. but that one won't be in my equation. And so your choice of your reference point is a powerful choice to try and simplify the problem. I could have picked a point up here to be my reference point, and if that was true, then these two forces would not contribute to the net torque because their R value, their distance from the pivot point is 0, so they contribute no torque. And so based on the problem, it's judicious to select a reference point about which you're going to measure the torque, or in other words, where you're going to measure this R value from. But remember, you have all of this to your advantage. This is a one-dimensional. You only get one equation out of this because it can either be clockwise or counterclockwise. But this you have for each dimension that you show. In this case, we have X and Y.